So the topic of today's webcast is SIMULIA for design engineers, and specifically linear structural validation app. What is this all about? So it's a finite element. Well, first of all, what is a SIMULIA? SIMULIA is a brand. CATIA is a brand, Delmi is a brand, SIMULIA is yet another brand of the SO portfolio. And it's all about simulation, behavior, stress analysis, etc. And in 3D Experience SIMULIA, it's a FEA, finite element analysis based virtual test tool. What is good about finite element analysis? It's applicable to models of virtually any shape or size. It enables design validation optimization prior to manufacturing. It actually may eliminate the need of physical testing altogether and shortens product development cycle. What does 3D Experience platform brings to the table? Well, first of all, it's a platform. So all the applications, all the brands, everything they have unified user interface. So it makes it a lot easier to navigate, to find all those icons and toolbars, etc. Secondly, it delivers fully associative design and simulation domains. No need to ever transfer files, export files, import, etc. It's all integrated. It provides simulation data management, so you can easily, because all your results are stored in the database, so you can search for them, open up later on, review, etc. And now what's different? Okay, so in CATIA v5, many of you might be aware of the module called, a workbench called GPS, Generative Structural Analysis. In 3DX, it's gone. What happened some years ago, the SO acquired a company called Abacus. And in 3DX, the solver is Abacus, which brings certain challenges because Abacus is a fairly complicated animal. In general, full-blown Abacus would be good for experts. So the SO-face challenge, okay, what do we do? How do we deliver the functionality to a more casual user, like design engineers, non-experts, non-specialists and stuff? So what they did, they implemented a bunch of roles, from simplest to the more complex ones, okay? So at the bottom of the food chain is a structural designer, then goes structural engineer, then structural performance engineer, structural mechanics engineer, and then finally structural analysis engineer. So those roles, SLL, SFO, SSU, etc., they essentially implement the Abacus methodology, which is your simulation is split onto simulation steps. It's like a history, and every step has initial conditions, the loads which develop in time, and boundary conditions, etc. But also there is a SRD, which is structural designer role. This is for design engineers because it's easy to use. It enables quick evaluation of strength and stiffness of products components, but it's limited to linear simulations only. So it's very, very user-friendly, and that's pretty much what we're going to look at this webcast. So, we're on slide. Linear structural validation. It includes simulation capabilities for the conceptual and early stage design. And the intended users are design engineers rather than experts. Like I said, it's very user-friendly, reduces the need for the user to understand the complexities of the underlying simulation technology. The tools and options are intuitive and explained in the language of product designers, while the complex features are automatically applied behind the scenes. And there is a guidance about the task, so there is never any confusion as what to do next to complete the simulation setup. And the simulation results are associated with the product and managed in the PLM database. So what kind of simulations you can do with this app? Linear static. But it's limited because nonlinear material models such as plasticity or hyperelasticity, etc., it's not supported. Large displacement deformation are not supported either, and finite sliding contact is not supported either. The other types of analysis are buckling, natural frequency, and steady state thermal. So how do you find this up? Well, the usual way, you go to the compass, you can do the search, and here it is, linear structural validation. Okay, so from here on, we're going to jump into a demo, and I'm going to show you live in the, what exactly you can do with it, how it works, etc., etc. So let me go to my 3D experience. So that's the part I'll be working with. And the first step, typically, I mean, it doesn't have to be done in a very particular order, but typically what I would do is apply material. And ideally, with the 3D experience, you would have your material definitions already defined and stored in the database. So you just search, find the material that you need, and apply it to your part. Now, I don't really have material database, so I'm going to show you how to actually create material definition. But before I do that, I recommend changing settings, specifically units. So let me go to the preferences. Okay. And in the common preferences, that was parameters, measures, and units. So what I recommend is, let me find stress, okay? The default units are pascals, which is Newton per meter squared. Not very useful units, I prefer MPa, megapascals, that's kind of a lot more easier to understand, kind of quantify, etc., etc. But I have it set already. So whenever you do this kind of stress analysis, I do recommend using megapascals. Can you use other units such as PSI, etc.? Of course you can if you want to. Now, material definition. Let me create one. And to do that, I need to start the material definition app. Okay, so I'm gonna go in here. Material definition. Okay, now, what's changed in 3D experience as far as materials? Like in CATIA V5, you had a material catalog, material library. It's just essentially one file. And materials in V5, they serve two distinct purposes. The first being providing mechanical properties, such as Young's modulus, Poisson ratio, etc. But the second was to provide the visual properties, texture, reflection, color, etc. They did change it in 3D experience, because now in 3D experience, they differentiate between core materials and covering materials. So the core material essentially is the material your part is made of. And covering material is what it's covered with. It could be coating, it could be paint, it could be anything. And covering materials, they define visual appearance only. And structural material properties are captured in the simulation domain. So let's say that's going to be aluminum. I'm going to call it, how I'm going to call it, let's say aluminum. I'll use unique, let's say just my initials. Okay, so now I'm in the app, and here we have options: create material, duplicate materials, but I want to add domain. Okay, so I don't need appearance domain, I don't need drafting domain or either. What I need is simulation domain, because all the structural properties are captured in the simulation domain. Okay, let me hit that, material simulation domain. Okay, I'll leave the default name, I can change it, of course. Okay, hit OK. And here's material simulation domain. Now, to put in valid mechanical properties, just double click. Okay, and we're gonna do structural analysis. So I'm gonna go into structural. The first one is general options, and you need to set up density. So density for aluminum, let me see, what was it, 2710. 2710. Okay, optionally you can set up proof stress, the yield. So you may ask at this point, okay, if it's a linear analysis, the plasticity or post-yielding behavior is not simulated. So why the yield stress? It's only used in the post-processing stage or when you visualize results to calculate factor of safety. We'll get to it once we get there. So for proof, I'll use 95 MPa. Okay, now let's go to Abacus Multiphysics. Again, I'll open it up. Mechanical, elasticity. So it's elastic material. Okay, so optionally, I can make it temperature dependent if I want to. So basically, when you set up analysis, and you'll see later, you see what is called initial temperature. And initial temperature affects which material properties are used. So in this case, okay, I'm not going to use temperature dependent. I'll use just Young's modulus. And that was, what is it, 70,000 MPa. And Poisson ratio was, I believe, 0.346. That's pretty much it. Okay. You see, there is a lot more, like, plasticity, viscoelasticity, damping, hydrodynamic, and on and on and on and on. But they are of no use in linear structural simulation. So pretty much the minimum I need for linear is what I did. Okay, hit OK, and it done. Now I need to apply it. How do I do that? Right click, apply. Okay, so at this point you want to go back to your part model and select the part body and just confirm. That's pretty much it. Okay, so I got material applied. See, it's applied on the product level. It's not on the simulation level. So, but let me go into the simulation now. I'm gonna click the compass. I'll do a search. So that's linear structural validation. So it's gonna ask you, okay, how you wanna name your simulation. Of course, it's useful to, use some meaningful names. I'm not gonna bother to do that. It's just a demo, so I'll just hit OK. All right, so it creates a new object, which is physics simulation. I don't want to use the word file because 3D Experience, they don't want us to use the word file. In the end, in the database, yeah, there are files definitely, but they want us to call it object. So it's a new object in the database. Okay, these are types of analysis. I'll stick with the structural. Hit OK. Okay, so I'm going to close this for now. Assistant will talk about it later, and I'm going to display the tree. Okay, so that's physics simulation. It has several headings: the model, the scenario, and the result. Okay, and it puts me into the scenario stage at this point. And I can start applying, properties, etc. But usually what you want to do is take care of the mesh first. So I'm going to go into the mesh. And what's good about 3D Experience meshing as opposed to GPS? In GPS, the default mesh usually would not give you good accuracy. But in 3D Experience, in linear structural validation, the default mesh is usually pretty good. If you're not happy with the default mesh, you can always change specifications. Okay, and there are essentially two. Okay, let me expand it a little bit. Okay, and those two are element size and also elements per hole. Okay, so with elements per hole, it controls how many elements it puts around 360 degrees angle, which is applicable not just to holes, but to all rounded surfaces. Optionally, I can apply local specification. If I want to have a denser mesh at some locations, I can certainly do that, okay? And I can generate the mesh, okay? Is it okay? Okay, so yeah, you can, turn it around, rotate it. It looks pretty good. Okay, and to hide it, well, just hit hide. Okay, now I'm gonna bring up what is called Display Simulation Assistant. Okay, you can set up analysis using the tools in the action bar. You see there's initial conditions, connection, boundary conditions, loads, etc., etc. Or you can use what is called Simulation Assistant. Okay, Simulation Assistant is like kind of like a guide. So for beginners, it's probably a better way to do things. Okay, so it has certain sections like simulation domain, mesh specification, materials, and it puts those green check marks and others. So for instance, boundary conditions are not set up, so I can go in here and it gives me the options for the boundary conditions. Now, do I have to click in here? I don't. Just as well I can pick in the action bar. It's up to me, but it's just convenient. Let's say I'm gonna click clamp and I'll select a couple of holes. Let's say those 2 holes are fixed in my model. Done. Okay, what about loads? Well, I'm gonna apply, let's say, vertical force to those 2 holes. So I'm gonna click force, select support. Okay, now what about the direction of the load? It's different how it's set up in 3D Experience as compared to CATIA version 5 GPS. And the difference is that the direction of the load is always aligned with the W axis of the robot. Okay, so you see this axis, okay, and that would be the Z direction. But I want to apply the load in vertical direction. So here it gives me a bunch of tools to change orientation of that axis system. So the one I'm going to use here is kind of straightforward. I'm going to align the triad handle with the global axis system. I believe that's this one. Okay, now you see the Z direction is vertical. That's what I want, and I'm going to apply a load. Let's say 500 newtons. All right, so that's pretty much it. Now, if I look at the tree, I'm not seeing any of those loads and boundary conditions. So how do I control? What if I want to change the magnitude of the load or something else? That would be another thing that's called feature manager. Okay, so those entities don't show in the tree, but if I pop up the feature manager, I can change visualization status, or I can, edit, pop it up, change the magnitude, etc. So pretty much whenever you want to change your boundary conditions and load, you have to work with the feature manager. Initial temperature, we don't really need it for this simulation. That's this little symbol right here. Like I said, it only controls the material properties if they were temperature dependent, but I'll turn it off. I'm not using any temperature dependence properties, and that's pretty much it. So the next step, run a simulation. So I'm going to go into simulate, click simulate. Okay, so what happens here, it actually exports an Abacus file and then reads it and runs the solver on the background. So I'm going to click OK. It should take about a minute. Just need to wait. So you see launching simulation, preparing step, errors, warnings, information, and all this kind of stuff. Yeah, just have to wait. It should be under a minute. It's a pretty simple model. Activating results. Yeah, static simulation completed, and it automatically activates the results environment. Now here, you see this pull-down menu. By default, it displays one mesostress, but we're gonna start with, let's say, deformation, okay? So it shows the deformation of the part under the given load, okay? And if I want to overlay it over the undeformed model, I'm gonna go into here. No, it's not here, it's in the view, I believe. Where was it? Render is setting, okay. So I'll say show geometry as well. So now I can see both. I'll hide the assistant for now. And I can do things like such an animation, make it faster or slower. Let's make it a little faster. Okay, so that's your first type of result. You want to exit animation, just click exit. So another type of results, you can display displacements. Okay, now let me change this render settings. I don't want to show geometry. Okay, that's displacement. So under the given load, the maximum displacement was about 0.06 of a millimeter. Not too much. Well, let's take a look at another result. One mesostress. Okay, so I'm gonna pop up this show minimum maximum. Okay, and I want to know the maximum only. Okay, so the global maximum was 89.9, but here, if you recall, the proof stress was 95. So it looks like it's all good. But okay, I'm gonna erase it, and we're gonna check another result, which is factor of safety. Factor of safety. Now it compares the result with the proof stress. And again, I'm gonna go show minimum maximum. Now I want to see the minimum value. Okay, and the global minimum is 106. So if factor of safety is over 1.0, it means the material is predicted to hold. If it was below 1.0, that would be the material is predicted to fail, because the stress, it means the stress exceeds the proof stress. But just let's imagine, okay, let's imagine, I'm not really happy with this design. The factor of safety is too close to danger, too risky, and I want to change the design. Okay, so I'm going to confirm it. At this point, I need to go back to, I'm going to exit result visualization, and I'm going to need to go back to my model. Okay, so I'm going to go back to the part. Okay, and I have a parameter here which controls the thickness of the part. Right now, what is it? It's 5. Let's change it to 6, for instance. Okay, go back into the simulation. Does it update the results automatically? No, it does not. I have to run again. Okay, so I can run it from here using action bar instead of the simulation assistant. All right, again, hit OK, let it run. Yeah, like last time around, it took about, a minute or less. So I just need to wait, the simulation status. So when it runs the solver, there are two options. In case you're curious, you can run the solver locally on your local computer, or you can run it on the cloud, like a high performance cloud computing. For big tasks, big analysis, etc., definitely you would want to run it on the cloud, but I'm running it on the local one. Okay, so let's check out the factor of safety. Okay, and I want to see the minimum. Oh, yeah, now I see it's 146, 146. So it's way over 1.0, which means I'm pretty safe at this point. You know, I can rest assured the part is not going to fail under the given load. Okay, well, that's pretty much it with my demo. It took less than I expected, but just to summarize, okay, so 3D experience, it's Abacus. It's not GPS anymore. GPS is gone, it's obsolete. The challenge was that the full-blown Abacus is a very complicated animal. And I did teach Abacus nonlinear to some design engineers in the past. It was not very successful because many concepts are not that easy to understand, and you know, the people would struggle a lot. So what they did, they created those various roles, as I popped up on this slide, and basically, depending on the level of expertise, you can pick one or another role. Now, the easiest one is SRD, structural designer, like I said. This is the closest analogy to GPS. If I go one level up, structural engineers, okay, it does comprehensive linear structural analysis. Comprehensive means it, you know, nonlinear simulation steps and on and on and on. So it's a lot more complicated thing. And all the way to, you know, the last one, SYE, which essentially is an enhanced pre and post-processor FEA tool. Computation must be performed remotely on the cloud using tokens. Yeah, that's pretty much it.